wanted to welcome everybody to the Hydraulics and Power Generation FPDA webinar today. If you're new to our webinar series, welcome. Before we begin, I'd like to remind everyone to please keep themselves muted during the presentation. And if we have time, we'll open it up for questions. After today's session, you'll receive a short survey, and I would greatly appreciate your feedback. It helps us to improve our future webinars. This session is being recorded and made available on the FPDA website in the next couple days. Just to access that recording, go to the FPDA website, click on Education and select On Demand. Also, be sure to check our FPDA website. There's a lot more learning opportunities available before the end of the year. And so now I'll turn it over to Carlos. Is it Eilenfeld? Did I say that right?
Yeah, that's fine. Yeah,
okay.
Eilenfeld. You can call me that. There's no worries.
Okay, so and he'll introduce today's presenters. Go ahead.
Yeah, okay. So I'll just want to introduce shortly as our presenters, Luis and Jim. They are our guys that will be sharing their thoughts and their experience with you on this topic of energy generation. And I am the general manager from Atos. Many of you probably don't know our brand, as we are, I would say, as a boutique hydraulic manufacturer out of Italy. We just you're starting to develop our presence here in North America. Our core competence is in proportional valves, 100% digital, and as we have unique products in our portfolio, and we want to lead with technology. And the intention of this session is just to share the experience that these guys have, as Luis is our regional sales manager from the South, down in Texas. And Jim is our systems engineer that provides the support, the technical support for the North American continent. So they have plenty of experience, and we're glad to share this with you, hoping that as we are providing some value add, as we just started with the FPDA as members. We just came in as new members, and the thought is just to provide value for the association and for you. I hope that you guys enjoy the session, yeah. And I'll give over the speech to Jim and Luis. Go ahead, guys.
Thank you, Carlos. Hello, everybody. Hopefully you can hear me all right. If you have any trouble, please let me know. So my name is Jim Traeger, and today I'm going to start off showing you some important differences between the hydraulic circuits used in power generation and the ones that are more commonly used in industrial applications. I'm going to focus on circuits used for prime mover controls, since they're the most critical and unique in power generation hydraulics. What are prime movers? Broadly, a prime mover is an engine or turbine that drives the electrical generator. More specifically, it's the components that convert the available energy into the mechanical rotation used by the generator. In hydropower, the turbine converts the potential energy of water plus gravity into mechanical rotation. In wind power, the turbine converts the kinetic energy of the wind into mechanical rotation. And in steam power, the turbine converts the thermal energy of the steam into mechanical rotation. So what are prime mover controls, and what do we need to consider when designing the hydraulic controls for prime movers? Well, we use closed loop controls for precisely controlling the energy flowing to the prime mover, i.e. regulating the fuel. The controls also watch the resulting outputs of the prime mover, like the rotational speed of the turbine or the electrical output of the generator. When starting up a turbine, we need a controlled release of energy to get the generator spinning up to synchronous speed. This is the speed at which the generator's electrical frequency matches the grid's electrical frequency. And then when we're generating power, the prime mover controls need to make small changes to the fuel to help the generator support the grid. They'll be changing things like the real power output, which would be watts, or possibly even changing the reactive power, which is bars. The prime mover controls also need to cut off the fuel from the turbine, providing safe shutdowns under normal conditions and in emergency conditions. Removing the energy from the prime mover is critical. If we fail to stop or bypass the fuel going to the prime mover, it will spin out of control. So how do we handle faults on industrial equipment? Well, in general, the best thing to do when problems arise on industrial equipment is to stop the machine's motion as fast as practical. For closed-loop hydraulics with proportional valves, we choose valves with specific spring conditions. We choose spring conditions that cause oil to stop flowing. Then all we do is de-energize the valve or the valve's coils for a reliable way to stop motion on the machine. If we look at the top row of valves, we have spring-centered valves. Notice the two spring-centered conditions, and what do they have in common? These are the spool conditions that will stop motion on a hydraulic cylinder. All ports blocked, or P blocked with A and B to tank, are commonly used spool conditions in hydraulic circuits that stop oil flow, causing a cylinder to stop. The bottom row are some examples of some high-response servo proportional valves with fourth position failsafe. This fourth position is only possible when the valve solenoids are de-energized. And notice the fourth position spool functions are the same as the spring-centered spool functions. This fourth position is also designed to stop motion of cylinders in industrial hydraulic circuits. When it comes to the valves we select for prime mover hydraulic controls, we want a different type of failure mode. We don't stop the closed loop system that controls the fuel flow, as this will keep the turbine spinning. Instead, we want to move the hydraulic cylinders to a full closed position, effectively removing energy from the prime mover. When we select proportional valves for closed-loop hydraulic systems, we use a valve configuration that will give us full flow when de-energized, and generally this is spring offset. Typically, this will be a P to B, A to T configuration at rest. Shutting down prime movers is very critical, so we also design in redundant ways to shut down the prime mover. Sometimes we integrate a redundant hydraulic shutdown valve into the manifold with our main proportional valve, or sometimes we supply a separate trip lock that can be installed in the hydraulic lines between the proportional valve and the prime mover. We've even made trip locks that are triple redundant for the most critical shutdown circuits. And keep in mind, there will also be other ways to stop the prime mover which operate outside the closed loop hydraulics. We could close intake gates and hydro turbines to cut off water from the whole turbine system. We can apply brakes on wind turbines, which will stop the blades from spinning, even if the wind keeps blowing. Or we use blow-off valves on steam turbines to allow the steam to safely bypass the turbine. So what would happen on industrial equipment if it fails to shut down? The most common things would be damage to the hydraulics, damage to the machine tooling, or damage to the structure of the machine possibly. This could cause the machine to be out of operation, maybe causing days or weeks of lost production. There could be a possibility of minor injuries to workers, but we hope with proper guarding and limiting access to dangerous areas, these injuries are usually minor and rare. It is very rare in industrial situations that a failure to stop causes a total loss of the machine. It would even be more rare for a failure to damage other equipment in the building. When prime movers get out of control, we have much more serious consequences. We could get total loss of the prime mover and generator, possibly damage nearby units. We could even damage the building, up to including structural damage that could make the building unsafe to occupy. This could result in months or years of lost operation, possible serious injuries to workers, and even the possibility of loss of life. On top of that, we even risk environmental contamination or destruction. So here's an example. This is a wind turbine that's in a runaway condition. So as you can see, it's important to get far away. The centrifugal forces of turbines spinning too fast could cause the complete and sudden destruction of the whole entire unit. Here's a picture from a dam and hydropower plant. This shows the damage that can be done to nearby units, the damage that can be done to the building when prime movers get out of control. This is actually a very terrible accident that did actually claim the lives of a few workers in the plant. And here's the aftermath of a steam turbine that went into sustained overspeed. And we can really see there's nowhere safe in the building as parts were thrown off. There's holes in the wall and the ceiling that were potentially blades from the turbine that punched through. We see there's a large part of the shaft embedded in the concrete. Pretty bad situation. So, basically, in summary, when it comes to power generation, the most critical controls are going to be for the prime mover. They may be slightly different than the circuits we use in industrial hydraulics, but is generally in respect to the fail-safe conditions, the proportional valves, and the additional redundant circuits required. You need to respect the power the prime movers can unleash and follow the industry's best practices to avoid serious injuries. Okay, Luis?
Thank you, Jim. I'll go over the opportunities here. You go to the next slide, please. Okay, opportunities in power generation. It is recommended to get familiar or review relevant standards, such as ASME, IEC, IEEE, and ISO. Also, it is recommended to consult industry professionals for prime mover controls. And besides prime movers, there are many other hydraulic systems that need to service or upgrade, like pumps, filters, oil cooling, proportional and solenoid valves, cylinders and transducers and sensors. And these solutions can multiply by the number of units at the plant across the country or worldwide. Next slide, please. Opportunities in wind power industry. Primary controls for wind turbines consist of blade pitch controls, proportional valves, and blade pitch cylinders. There is a hydraulic power unit with piston pumps, accumulators, filters, and solenoid valves. Also, there is a oil cooling system that includes kidney loops and air coolers. And in addition to this cooling loop system, there is a lubrication system for truss and guide bearings with, again, with pumps, filters, and solenoid valves. So these are the main hydraulic components that are multiple, and there are multiple units in a wind farm. They need to be serviced. Here's a picture of the turbine, showing, starting from the top, the bearing housing, and then the gearbox, the gear oil cooling fan, and also there is a hydraulic power unit on the right-hand side, and there is the generator and the hub of the turbine. Next slide. Considerations for wind power equipment. There is a high vibration present on these units. The hub equipment rotates around 10 to 15 RPM. And there is a gearbox inside the nacelle that rotates around 1800 RPM. And also the nacelle rotates into the wind direction. The height of the turbines, these nacelles can be more than 150 feet from the ground. and equipment is installed by the cranes. And there is also equipment inside the nacelle that must fit through the hatches. So there is a space constraints. Every square inch of space is very, very critical. Here's a picture uh, of the hub showing the accumulators and a bank of accumulators. Also, there in the back of the accumulators, there are some pitch control cylinders. And at the bottom of the accumulator, there is a pitch control valve. And on the right-hand side, there is a control box. So, and all this is rotating while the turbine is spinning. Next slide, please. Other considerations for wind power equipment. These units are normally installed in harsh environments like dust storms, lightning, and hail, hurricanes, and also temperature are extremes. They are in remote locations, and service teams may be hours away. They have automated starts and stops, also many sensors to monitor the conditions, and there is a SCADA communication systems to relay information. Again, here's another picture showing the blades on top, the hub that is rotating, the main shaft bearing, and the housings. And there is some control boxes. The nacelle is pretty much the housing of the turbine. And there is a generator, also the mechanical brake. And sometimes those mechanical brakes are hydraulic too. So the gearbox and the jaw system that rotates the nacelle. Next slide. Opportunities in hydropower industry. On prime mover controls, there are proportional valves and cylinders that operate wicket gate controls and blade controls. Also, hydraulic power units is installing these systems with positive displacement pumps, accumulators, and solenoid valves. There is a bearing lubrication systems also with pumps and filters. And for sludge gates, there are cylinders and solenoid valves that operate intake gates and spillway gates. The picture here shows some of the gates. There is a red line on the left showing the intake gate, and on top of the dam is the spillway gates. So they're right in the center. There is a turbine showing the wicket gates and blade control gates. Next slide. Consideration for hydropower equipment, they are in remote location areas and they are unmanned plants. Reliable and try and true solutions are required. Also knowledge of interface with the PLC and SCADA communication systems. For prime mover controls, they are all systems. They operate low pressures around 200 psi. Other common pressures are 300 to 600 psi. And they also have mechanical flow control wicket gates. For blackout and black stars, they have a 125 volt DC battery banks that runs most of the controls in these systems. Oil temperature in reservoirs, hydraulic reservoirs is rarely above room temperature. Again, here's another picture showing the wicket gate and the turbine blades. Those wicket gates, sometimes they have a cylinder dedicated for each wicket gate. Also, the turbine blades are adjusted by a hydraulic system. So, next slide. As far as opportunities in steam power industry, the prime mover controls have proportional valves that operate steam control valves, extraction valves. Again, also there's a hydraulic power unit with piston pumps, filters, accumulators, and solenoid valves. Also lubrication systems as well for truss and guide bearings. with pumps, filters, and sonar valves. Again, all these components are required to be serviced or replaced. Here's a picture of a steam turbine showing, indicating at the top the extraction control valve. Those are hydraulic, servo hydraulic driven. And there is a guide bearings on these units that require special lubrication. Next slide. Consideration for steam power equipment. Reliability is very important. Turbines run for weeks, months, non-stop, and sometimes owners pay if they have unplanned outages. And on prime mover controls requires to be specialized for the model of the turbine. They have a fast operation. Typical shutting down is around 100 milliseconds. Also, there is a redundant hydraulic trip blocks to ensure shutdown. Monitoring, lots of sensors for detecting troubleshoot before failure. And temperature of components on these hydraulic systems are commonly above 100 degrees Fahrenheit. So here's a picture of a turbine under service. Next slide.
All right, thank you, Luis. So I'm going to go back and start talking about these opportunities. You're going to find that you come across, you'll be dealing with a lot of obsolete components. The reason that these power plants have so many obsolete components is that they're expected to work for maybe 50 to 60 years. If you consider the payback of the initial installment is 20 years, 20 years, in 20 years' time, a lot can happen. Suppliers can go out of business. OEM parts and service may not be available. However, you may find that small niche companies, possibly made up of former OEM employees, could pop up to fill the gap. And obsolete components are really just a normal thing, considering that technology never stagnates. New technology is always going to cause old technologies to go away. When working with obsolete components, it's important to consult industry experts, especially on the prime mover controls, as that's the most critical aspect of the generator. But you can gain some knowledge about these industries by visiting industry-specific trade shows. That can allow you to make some global contacts, find some people that are knowledgeable, and maybe willing to share some of their ideas or some of their past experiences. These trade shows will also help you understand what some of the best practices are in the industry. A lot of these industries have reliable, tried and true solutions that they like to keep reusing that just maybe need to be brought up or built a similar way with modern equipment. It's also a great idea with these trade shows that we can share ideas for improving on the reliability and availability of the existing equipment. You may find that seasoned power gen guys, they're actually interested in a lot of the new technology. And a lot of us industrial hydraulic guys are usually at the edge of the new technology. I find that power gen is actually really interested in upgrading to new digital products. They may be more flexible and not so custom designed for certain units, but digital products that are programmable can be a bit more flexible. They're also more interested in industrial communications, different field bus communications, other industrial protocols for transmitting information and data to control centers. It's also very interesting for these power gen guys. So when you're replacing obsolete components, be prepared to make compact, customized designs. A lot of times because you're going to have space constraints that are actually really critical to the success of the project. Wind turbine nacelles are tiny. They have small hatches you need to get into. Hydropower is geographically constrained and can have odd shapes or space constraints. You'll find you have to make custom adapter plates because you're going to reuse existing parts of the equipment. Some of the larger equipment, the older, more expensive equipment gets reused while the control systems are upgraded. So making custom adapter plates is pretty much required on a lot of these projects. And what I also find is that a lot of people like to use off-the-shelf components of these upgrades. It really is kind of a win-win. Excuse me. It can be a win-win for both the end user and you. Using off-the-shelf components can reduce a lot of the design time working on these power generators. And it also makes future upgrades easier because they already are designed to work with products that maybe have standard mounting interfaces, standard electrical interfaces. It also helps make lead time shorter for spare parts. So in conclusion, power generation offers a lot of opportunities for hydraulic sales. You should be knowledgeable about industry-specific concerns before you get into it. You're definitely going to want to consult industry experts so that your projects are as successful as they can be. If you want to get into the power gen industry, best way is to start getting involved with industry-specific trade groups and maybe start identifying new trends and see ways that you can add to that trend or maybe develop new trends. And always be constantly looking for ways to implement new technology. Even though these industries can be very old, new technology is also very welcome in a lot of power gen situations. So with that concludes the presentation.
All right, thank you. Does anyone have any questions? Looks like there are none.
Yeah. Okay, then I would like also to thank you all also for participating in this meeting. As I said, as we would like to be an active member of the FPDA and provide as a share as our experience as with you guys. We are a technology-driven organization, and if you have any problems that you may feel that we can help, we are glad to help. Yeah, and I would like to thank you for your interest, and also Kathy, particularly for you, for the organization. It was really great. Great experience. Yeah, and thank you all for that. Yeah, all my best. Have a wonderful rest of your week.
Thanks, everyone.
Thank you, Carlos.
Bye
Thank you.
bye.
I appreciate everybody's time. Thank you very much.
Thank you.
Bye bye.